All right, we're going to take another look at the chain rule, and we're going to dive a little bit deeper into how you can take advantage of the way that the chain rule can be written, both in Leibniz and Newton notation. It's actually quite remarkable and can make some particular questions a lot easier to work through. So remember, of course, that the chain rule is dealing with taking the derivative of a composite function. So here's a composite function, f of g of x. A real simple situation here is think of f of x as being the square root of x and g of x as being, x squared plus 2. So the composite function would be the square root of x squared plus 2. And we, of course, know that when we take the derivative of this, we have to take the derivative of the outer function, keeping the inner function the same, right, with respect to the inner function, and then take the derivative of the inner function, g of x, with respect to x. So that looks like this. So, just to recap, taking the derivative with respect to x of f of g of x, or also written f of g of x prime, can be found by taking the derivative of f with respect to g, the outside function, times the derivative of g with respect to x. Now that's all well and good, but when we represent the chain rule using Leibniz notation, we can actually see it in a way that can sometimes be a little more useful. Leibniz notation is, of course, where we represent the derivative using the differentials of y and x, dy and dx, to represent the derivative at any point or the slope of a function at any point. So to do so, let's rename our functions f and g. So let's think of f as being the function y, and y happens to be written in terms of another function of x. In other words, u. So we have y, and it's written in terms of u, and u is a function of x. Now, if I want dy dx, I need to take the derivative of y with respect to u, and also the derivative of u with respect to x. In other words, if I want dy dx, I need to take the derivative of y with respect to u and multiply it by the derivative of u with respect to x. Now, the cool thing about representing the chain rule in this way is we can sort of view the derivatives as these fractions. Now, that's not totally mathematically correct. There's some nuance there that makes it not, that they don't behave exactly like fractions, but for our purposes, this is pretty clear here, right? I have dy du times du dx. So this is the infinitesimally small change in y over the infinitesimally small change in u, and this is the infinitesimally small change in u over the infinitesimally small change in x. So you can notice here that the du's seem to sort of, cancel each other out, right? Du over du is just 1. And that leaves us with dy dx. And this works perfectly fine. And so viewing the chain rule in this way can make quick work of some, derivative problems that might at first seem sort of complex. Let me give you an example. All right, so here's a fun little example. Y is equal to x squared plus 1, and u is equal to 3x minus 2. Your goal is to find dy du. Why don't you give this a try on your own, and then we'll take a look at it and see how the chain rule makes really quick work of this problem. All right, so what we notice here is we're looking for the derivative of y in terms of u. And what we see here is that y is a function of x, and u is a function of x. So you're thinking to yourself, okay, well, how can I get dy du? What can I find easily? Well, I can find dy dx. Okay, that's good. I can find dy dx. So if I have dy dx, what then would I need to multiply that by in order to get dy du? Well, it's not too hard, right? What I need is dx du, and when I multiply that, I'll end up with dy du. So let's go about finding these derivatives here. The derivative of y with respect to x is easy to find. I'm simply going to differentiate this equation with respect to x. So dy dx is going to be 2x. Not bad at all. right? Now I need dx du. And this is where it gets a little tricky. Here I can differentiate with respect to x, and I can get du dx pretty easily. But I want dx du. Now remember, if we're thinking about this in terms of acting like fractions, if I can find du dx, then I can just take the reciprocal of it, and that will be dx du. Let me show you what I mean. We'll take du dx here, derivative of u with respect to x, and that's simply going to be 3. Which means, of course, that if I take dx du, that's the reciprocal, or 1/3. Which means that this piece over here is 1/3, and so I have 2x times 1/3, which leaves me with 2/3 x. And that's the derivative of y with respect to u. Now you may be saying to yourself, that's weird. I would expect the derivative of y with respect to u to be in terms of u. And you can write it in terms of u if you want. You just need to solve for x in terms of u. That's perfectly fine. But this is a totally appropriate answer. If they ask for the answer in terms of u, then you can make that substitution for yourself. The purpose of doing this is simply to see how we can use the chain rule and the concept of the derivative acting very similar to a fraction to make easy work of a problem like this. I do want to point out an alternative way to find the derivative of y with respect to u, which some of you may have thought of, and I'll do this down here. What you're thinking to yourself is, okay, I want dy du. I currently have y in terms of x. How could I get y in terms of u so that I can just take the derivative? Well, luckily, I have a relationship between u and x. And so if I solve for x in terms of u, then I can plug that back into my function over here, and I have a y in terms of u function, and I can differentiate that. Now that's perfectly fine, and let's go ahead and do that now. So if I'm going to solve this here for x, I'm going to end up with u plus 2 over 3. And using this, I can then rewrite my function y. Y is going to be equal to u plus 2 over 3 squared plus 1. Now, I'd have to differentiate with respect to u, and notice, of course, that you're going to end up using the chain rule anyways. You'd have to take the derivative of the outside function, which is something squared, and then take the derivative of the inside function. Okay, so it ends up actually being a little bit more work, obviously, but if you do so, you will end up with 2 times u plus 2 over 3 times u over 3. And you can certainly simplify this, and I will let you make the substitution back in for x using the fact that u equals 3x minus 2, and you can show yourself that you end up with the exact same thing, which is 2/3 x. All right, if you want to practice on a problem from the test, go ahead and take a look at number 25 from the most recent practice test, and you can try implementing this strategy that we discussed up here on your own and see how much easier it is than doing this whole thing down here. All right, I hope that was helpful. Remember, this is a really neat way to represent the chain rule that can be extremely useful. It's just as helpful as understanding the chain rule in this way. But regardless, it is important to understand the chain rule as much as possible because it certainly will be on your test.